Tonight we're drifting toward a place most of us will never visit, though we've all imagined it at some point, usually wrapped in images of endless snow, frozen winds, and a horizon so wide it almost feels like it could swallow the sky. We're heading south, far south, to the bottom of the planet, where Antarctica spreads out like a white continent of secrets. And not just the well-known kind, like penguins wobbling across ice, or towering glaciers that look as if they've been carved by an oversized chisel. We're exploring the hidden, unreachable, stubbornly untouched parts of Antarctica that humans may never set foot on at all. It's a strange thought, isn't it? The idea that there are places on Earth that remain out of reach. In an age where satellites photograph every coastline, drones weave through remote forests, and explorers dive into submarine trenches miles beneath the waves, it's easy to imagine we've finished mapping the planet. But then you look toward Antarctica and realise the story isn't quite finished. There are pockets of land, caves of ice, buried valleys, and shifting terrain that resist us not because we lack curiosity, but because the environment itself has drawn a line and simply said, no farther. Before we wander into that frozen quiet, I'd love to know something simple. Where in the world are you listening from tonight? And what time is it for you right now? Feels fitting somehow to ask about your place on the map as we talk about places that barely belong to any map at all. Your corner of the world might be warm or busy, or wrapped in the late evening calm, but right now it's connected to this distant continent through nothing more than your attention and a bit of imagination. If you find these late-night explorations soothing or interesting, or if they help you unwind after a day that felt a little longer than you expected, I'd be grateful if you'd give the video a like or maybe subscribe so more people might find a small pocket of calm here. It helps our sleepy corner of the internet grow quietly, like a lantern in a long hallway. And with that, settle in a little. Let your shoulders drop. Let the day shift behind you for now. Because for the next while we're travelling into a world of ice that has its own rules, its own patience and its own ways of keeping secrets. A world where sunlight can linger for months or vanish just as long. Where the air can be so cold it feels like it might shatter if you breathe too quickly. And where massive regions remain so unreachable that even pondering how to get there becomes an expedition of its own. Antarctica sits at the bottom of the globe, but the more you learn about it, the more it feels as if it stands apart in other ways too. Most of the world is shaped by familiar cycles. Seasons, storms, tides, migrations, growth. But down there, those patterns twist into something different. Summer doesn't bring warmth so much as it brings the ability to endure the cold. Winter doesn't simply darken the days, it erases them. Entire months pass without a sunrise, and the only constant is the wind scraping across the ice. Researchers who spend a season there talk about the quiet not as peaceful but as enormous. A kind of quiet that seems to rest over everything like a blanket. And beneath that quiet, the landscape behaves in ways no other place does. There are mountain ranges completely buried under ice sheets taller than skyscrapers. Valleys sealed away since long before humans existed. Lakes that sit in total darkness, warmed only by the faint internal heat of the earth, never touched by open air. Many of these places aren't just remote. They're locked away by the very nature of the continent. You can't walk there. You can't land a plane. You can't safely send a rover in most cases because the ice is constantly shifting, cracking, collapsing, and rebuilding itself. Even satellites can only hint at what lies underneath. It's a continent that protects its mysteries with a stubbornness unmatched anywhere else. But what makes this all the more fascinating is that our difficulty in reaching these places isn't for lack of trying. Humans have managed to get to the bottom of ocean trenches. We've climbed peaks so high they scrape the edge of breathable air. We've drilled into Earth's crust and even landed on the moon. Yet there are still regions of Antarctica where no one has walked, no one has studied up close, and perhaps no one ever will. These places are so inhospitable that they push technology, engineering and physical limits past the point of breaking. Some of them sit under ice so thick that the weight alone would crush most machines. Others lie beneath ice shelves that could fracture at any moment or under winds so strong they can flip vehicles. And even if we could technically reach them, there's the question of whether we should. The more you look into Antarctica, the more it becomes clear that it isn't just a frozen land at Earth's edge. It's a living system, constantly shifting in slow, quiet ways that shape the entire planet. The ice breathes in the sense that it grows and shrinks with the seasons. The winds circle the continent like a protective ring. The ocean beneath the ice is home to ecosystems that might hold clues to early Earth, or even life beyond our planet. And those untouched areas we're talking about may contain information too fragile to disturb. A footprint, a piece of equipment, even a slight change in temperature could alter something that's been preserved for millions of years. And that brings us to the heart of why some parts of Antarctica may never be explored. It isn't just danger or cold or the limits of our equipment. It's also about respect. The continent is protected by international agreements that prioritize research, conservation, and peace. No drilling without extraordinary justification, no mining, no military activity, no disturbing wildlife. And while exploration is allowed, there are strict rules to ensure the environment isn't damaged by human presence. When you combine these limits with the physical challenges, you end up with regions where the only sensible choice is to leave them untouched. Still, even knowing this, the idea that vast areas of the planet remain unseen by human eyes feels unusual. We're used to information being a tap away, satellite images available in seconds, the entire globe mapped with precision. Antarctica is a reminder that not everything is accessible. Some places don't reveal themselves easily. Some places push back. And strange as it might sound, that resistance is part of what makes them worth thinking about. Because when something can't be reached, it forces us to acknowledge that the world is still bigger than our ability to grasp it. Imagine a stretch of ice so large and so thick that it hasn't melted for millions of years, hiding mountains taller than the Alps underneath. Imagine a network of subglacial lakes sealed away in total darkness, unreachable not because of depth, but because the ice above is too unstable to drill. Imagine valleys carved by ancient winds, but filled in by layers of snow and ice that move at a pace too slow for the human eye yet too powerful to resist. These are not exaggerated stories. They are real locations that scientists know exist, but cannot get to without risking machinery, teams, and the delicate balance of the continent itself. For a moment, think about how unusual that is. The Earth you know, the one with highways, cities, farms, coastlines, forests, deserts, is only one version of the planet. Then there is this other version far to the south, a version shaped by temperatures colder than anything most people will ever feel. A version where ice doesn't just cover the land, but becomes the land. A version so remote that even the simplest tasks, walking, breathing, seeing, are shaped by the environment's conditions. When people arrive at a research station for the first time, they describe feeling as if they've stepped into another world entirely, one that operates on rules they have to learn slowly, carefully. The deeper we go into this topic, the easier it becomes to see that Antarctica defies the usual idea of exploration. You can't just set out with good gear and determination. You can't simply upgrade technology and assume success. The continent sets limits, and it does so unapologetically. And in some ways, that limitation feels strangely grounding. It reminds us that exploration isn't about conquering everything. Sometimes it's about understanding when to pause, when to observe without intruding, when to acknowledge that a place's isolation is part of its identity. And now that we're standing at the edge of this idea, this continent with its unreachable spaces, we can start moving a bit deeper into what those spaces actually are and why they remain beyond our reach. The ice itself holds some of the answers, and it behaves in ways that shape everything around it. It isn't static, and it certainly isn't simple. It changes constantly, forming patterns that don't care about our curiosity or our plans. And if we want to understand why some parts may never be touched by human presence, we have to understand what the ice is doing. We'll take our time with that, easing into the next part the way someone steps onto a frozen lake, slowly, listening carefully, because the ice of Antarctica is more than a surface or a barrier. It's a moving, shifting, restless force that shapes the very idea of what exploration means. Let's wander a little deeper into that next. The farther you travel into Antarctica, the more you begin to feel the limits of what a map can do. A map promises clarity. Lines, borders, shaded regions, tiny symbols that say, here is land, or here is sea, or here is something you should know about before you go stumbling into it. But when it comes to the southernmost continent, maps start to lose their confidence. They offer outlines and approximations. They gesture at features buried under thousands of meters of ice. They do their best, but in truth they can only hint at what lies beneath the surface. And in many places they don't hint at all. They simply go quiet. This is where the known world begins to fray at the edges, where cartography meets uncertainty, and the white spaces on the page aren't just empty, they're honest. They're admitting that humans haven't fully reached these areas, haven't measured them, haven't walked across them, and perhaps never will. In a way, these blank regions aren't failures of mapping. They're markers of reality. They show the places where the land refuses to sit still long enough to be pinned down, where the ice moves and reshapes itself faster than we can study it, where the landscape is so inaccessible that drawing it accurately becomes a kind of guesswork. You can imagine the early days of Antarctic exploration, when people tried to map coastlines while battling winds that could knock a person over with the ease of brushing crumbs off a table. Those expeditions weren't dealing with satellite images or GPS. They were confronting cliffs of ice taller than any building they'd ever seen, open water that could freeze solid overnight, and distances that stretched farther than their supplies could carry them. They could fill in only what they could see, and even then the ice sometimes shifted between the time they arrived and the time they left. This left cartographers with an uncomfortable challenge. How do you map a continent that doesn't behave like a continent? Even now, with technology that can measure the height of a grain of sand from orbit, Antarctica continues to resist being fully understood. Some of that resistance comes from the thickness of the ice. In many places, the ice sheet is more than 3 kilometers deep. That's enough to swallow mountains whole, enough to hide entire landscapes that modern humans have never glimpsed directly. Radar can peer through some of it, but not all. And even the best readings can be distorted by layers of compacted snow, internal reflections, or the ice's constant motion. So while radar images give us a rough idea of what lies beneath, the details remain uncertain. The shapes of valleys, the exact placement of ridges, the depth of ancient basins, those things are often approximations. There's also the issue of the coastline. It might seem strange that in the 21st century we don't have a perfectly defined outline of Antarctica, but the truth is that much of the continent's edge isn't land at all. It's ice shelves, thick slabs of ice floating on the ocean. These shelves can be hundreds of kilometers long, stretching outward like frozen balconies, and they are constantly changing. They grow as snow accumulates and pushes older ice outward. They shrink when icebergs break away, sometimes in pieces larger than small countries. The coastline shifts not in inches or meters, but in massive chunks that can alter the shape of the map in a single season. When explorers first traced these coasts, they weren't drawing the land. They were drawing the ice, and that ice is always on the move. In some cases, the coastline they mapped doesn't exist anymore, replaced by new formations or open water. Modern maps try to correct for this, but the corrections come with disclaimers. A modern map of Antarctica is more like a snapshot than a fixed truth. It shows a moment in time rather than a permanent boundary. And then there are the areas that defy mapping not because of ice thickness or shifting shelves, but because reaching them would require crossing terrain so dangerous and unpredictable that even the most advanced equipment struggles. Think of crevasse fields, vast regions where the ice is cracked open by its own movement. These cracks can be shallow or enormous. Some extend hundreds of meters down, forming deep blue chasms that look solid from above but are covered by snow bridges barely strong enough to hold a bird, let alone a vehicle or a person. In satellite images, these areas often look harmless, like flat expanses of white. But on the ground, they're traps waiting for the slightest weight. Machines can fall into them without warning. Ropes snap, sensors fail, and the deeper you go into Antarctica, the more frequent these crevasses become. This is one of the main reasons maps of Antarctica have blank spaces. The ice doesn't just sit still and wait to be recorded. It pulls apart and slides and melts and refreezes. It behaves like a slow river shaped by gravity and pressure, and it reshapes itself every moment of every day. A map might show a smooth region in one year and a minefield of crevasses the next. Even researchers who work in Antarctica describe this as one of the most unnerving aspects of the continent. The ground itself refuses to behave like ground. But even setting aside the ice, the sheer scale of Antarctica would challenge any attempt at full exploration. It's larger than Europe. It's roughly the size of the United States and Mexico combined. And instead of highways or cities or outposts scattered evenly across the surface, there are only a handful of research stations separated by distances so vast that travelling between them often requires specialised aircraft, and even those can fly only in certain conditions. A storm can ground flights for days or weeks. A temperature shift of just a few degrees can make a runway too brittle or too soft. And during the long winter months, darkness covers the continent entirely, making aerial navigation nearly impossible. Imagine trying to map a land where half the year is night and the other half is a blinding glare of sunlight bouncing off endless white. Imagine trying to travel across areas where the wind can erase footprints within seconds, where visibility can disappear without warning, and where compasses become unreliable so close to the magnetic pole. Even with GPS, the elements can interfere with signals, equipment can freeze, batteries can fail, and communication can drop unexpectedly. All of these challenges create regions where mapping is incomplete, because even approaching them comes with risks that outweigh the benefit. And beyond the technical obstacles, there's a deeper question, one that researchers and conservationists have to consider carefully. Should every part of Antarctica be mapped? Should we aim to explore every valley and lake and ridge beneath the ice? The desire to know is strong. Humans have an ingrained urge to fill in the unknown. But Antarctica isn't like other places on Earth. It's fragile. Disturbing certain areas, even briefly, could change ecosystems or contaminate environments that have remained isolated for millions of years. Some of the blank areas on the map are connected not just to danger but to responsibility. Leaving them unmapped, untouched, and unseen might be the wisest choice. This creates a strange situation where the edges of the known world are not limited by our lack of imagination but by our understanding of consequences. Scientists know that drilling into certain subglacial lakes, for example, could introduce microbes or chemicals that would alter their pristine conditions. Entering some environments could leave behind heat or moisture that changes their structure. Even landing a drone in certain regions could leave residue that interferes with future observations. So the blank spaces persist, not just because they are hard to reach, but because reaching them might cause harm. The more you think about these blank areas, the more they start to represent something unusual in modern times. Most of the planet is accessible in some way. Even the deep ocean, though hard to explore, has been visited by remotely operated vehicles. The highest mountains have been climbed. The thickest forests have been surveyed. The driest deserts have been crossed. But Antarctica holds an entire category of not yet, and maybe never, that sets it apart. In a world that feels increasingly known, it maintains pockets of genuine mystery. You might think of someone looking at a map and seeing a blank spot as an invitation, a challenge, a mystery to solve. But in Antarctica, a blank spot can also be a warning, a reminder that some places don't need to be filled in, some places still belong to themselves, and some places might be better off staying exactly as they are, unmapped, untouched, simply existing without our interference. Still, these blank spaces don't remain empty in our minds. They spark questions. What kinds of landscapes lie beneath the ice? What ancient formations rest under the frozen crust? What stories could be told by sediments, rocks, or hidden lakes if we could reach them without altering them? These are the kinds of questions that shape modern Antarctic research. Scientists spend years analysing data from satellites and remote sensors, trying to understand what the ice is doing and what it's hiding. They build computer models that simulate the movement of ice sheets over thousands of years. They study the temperature of the land beneath the ice, the flow of water trapped below, and the gases sealed inside ice cores. All of this helps fill in some of the gaps without ever disturbing the regions themselves. In this way, the blank areas on the map aren't ignored. They're studied from a distance, understood indirectly, respected for what they may hold, and in a fitting twist, sometimes the best way to understand a place is to leave it alone. But if we're to understand why certain regions may never be explored directly, we need to look more closely at how the ice behaves. The land beneath Antarctica might be ancient, but the surface is always in motion. It moves with a slow, relentless persistence that doesn't announce itself loudly, yet reshapes everything. And this movement is one of the main forces that keeps parts of the continent beyond our reach. The deeper we go into this idea, the clearer it becomes that Antarctica isn't just unmapped in places, it's unmappable in the traditional sense. The terrain won't stay still long enough to be captured. The ice doesn't want to cooperate. It changes shape, direction, and texture as if responding to its own silent instructions. To understand why, and to understand what this means for the areas that remain unseen, we need to look at what the ice is doing beneath our feet. That will take us into the next stretch of our journey, where the surface begins to behave like a living force, and exploration becomes something far less predictable. Let's continue a little further, where the solid ground becomes something more complicated. When people picture Antarctica, they often imagine a huge frozen plain, unmoving and quiet like a sheet of glass that's been chilled into permanence. But the longer you look at the continent, the more you realise that the ice isn't still at all. It shifts constantly, not with dramatic speed or loud motion, but with a slow, steady force that works every hour of every day. There's something almost misleading about its calm appearance. What looks like a motionless field is actually a frozen landscape sliding across the continent in ways that reshape everything in its path. And this movement is one of the main reasons certain regions can't be reached and might never be explored directly. The best way to think about it is to imagine standing on what feels like solid ground, while that ground is actually creeping forward beneath you. You don't feel it, you don't hear it, but it's happening. Massive ice sheets, some taller than mountains at their thickest points, slowly spread outward under their own weight. Gravity pulls them toward the coast, and while the speed varies, some places shift mere centimetres a year, others several metres, the entire mass is in motion. It behaves more like a very slow river than a rigid surface, and the older the ice, the more it has travelled, sometimes crossing hundreds of kilometres over many thousands of years. This movement starts at the heart of the continent, where snowfall accumulates year after year, building layers that compress into dense ice. As more snow falls, the pressure increases, and the older layers begin to deform, first bending, then flowing outward. It's not like water rushing downstream, but more like thick cold syrup sliding across a table. The ice stretches, cracks, compresses, and continues its crawl as though following a rhythm set deep within the continent. It's steady, predictable in a broad sense, and unstoppable. That slow progression is what feeds the giant ice streams and glaciers that reach toward the coast. But in the interior, far from where the land meets the ocean, the movement can be even stranger. You might expect that the interior of Antarctica, far from the cliffs where ice breaks off into the sea, would be calm and stable, but that's not what researchers find. Beneath the thickest parts of the ice sheet lies a network of warped landscapes, ridges, valleys, hidden basins that influence the direction of the ice above them. The ice flows along these features, speeding up or slowing down depending on the terrain. Where the land beneath drops suddenly, the ice can move faster. Where the bedrock rises, the flow slows. This creates tension in the upper layers, causing cracks to form. These cracks can become deep crevices that open and close as the ice flexes. For anyone trying to traverse these areas, the effect is unsettling. A region that looks flat from above might hide a complicated internal structure. Snow can drift across the top of crevasses and create thin layers that appear solid, but are anything but. A single step in the wrong place could break through to a cavern of blue ice stretching downward farther than the eye can follow. Even heavy vehicles built for polar conditions aren't safe in some places. They can fall through without a moment's warning. The ice shifts enough that routes used one season may be unusable the next. What was passable last year might now be riddled with cracks. What looked dangerous before might become smooth. The unpredictability isn't random. It's simply the result of ice acting like a slow-moving giant, stretching and folding itself across a vast landscape. These changing patterns are part of why some regions are considered nearly impossible to reach. The ground beneath can't be trusted. Even if researchers wanted to cross an area to gather data, they'd have to weigh the risks carefully. There are places where no one has attempted to travel simply because the ice is too unstable. The continent decides where people can safely go, and it doesn't give many invitations. The movement isn't limited to the ice sheet itself either. There are enormous ice streams, channels of fast-moving ice that function almost like highways within the larger sheet. These streams flow many times faster than the ice around them. In some cases, they can move hundreds of meters in a single year. That may not sound fast, but for ice several kilometers thick, it's remarkable. And because these streams flow so quickly, they carry fractures and crevasses with them, churning up the surface in ways that look chaotic from above. Navigating across them is extremely dangerous. You could spend days doing nothing but probing the ground ahead, testing each step, only to find that the ice has shifted again by the time you return the next morning. What's even more surprising is that the ice doesn't just move horizontally. It also rises and falls. Changes in snowfall, temperature, and the flow of the ice sheet can cause the surface to lift or sink. Some regions experience vertical movement that would be obvious if we could see it happening in real time, but because it unfolds over years or decades, it stays invisible to the naked eye. The continent behaves like something that breathes, expanding in places and collapsing in others. To a satellite, these changes are measurable. To a person standing on the surface, the ice looks exactly the same as it did before, even though it's shifting beneath their feet. Underneath all of this movement lies another important factor, the bedrock itself. Unlike the continents we're used to, solid ground anchored firmly in place, Antarctica's land is influenced heavily by the weight of the ice pressing down on it. In some regions, the ice is so thick and heavy that it has pushed the land below sea level. If the ice melted entirely, the continent would rebound upward over thousands of years. But for now, the land sits low, and water can collect beneath the ice in pockets and lakes. These subglacial lakes create slippery conditions that can accelerate the movement of the ice above them. Water acts like a lubricant. Where a lake drains through a crack or channel, the ice can suddenly speed up. Where water becomes trapped, it can change the shape of the ice sheet from below. This complex interaction between ice, water and rock makes certain areas incredibly difficult to study. Machines that drill down risk contamination. Rovers can't always identify stable ground. Satellite readings sometimes conflict because the ice's density changes from place to place. And even when equipment works perfectly, the subject being measured is always changing. That makes it challenging to gather consistent data. Every measurement is a snapshot of something in motion, and then there's an element that complicates things even more, the temperature inside the ice. The upper layers of the ice sheet are brutally cold, as you would expect. But deeper down near the base, the temperature can approach the melting point because of the heat coming from the Earth's interior and the friction caused by the ice dragging across the ground. This means that in some areas the bottom of the ice sheet is actually wet. This thin layer of water allows the ice above to slide more easily, and sliding ice tends to deform more quickly. It buckles, stretches, and moves in ways that make the surface unpredictable. In places where the base is frozen solid to the rock, the movement slows and the ice becomes more stable. But where the base is wet, the ice can surge forward unexpectedly. These surges can alter the terrain above, creating new crevasses or widening existing ones. They can also break apart layers of compacted snow, making the ground uneven and dangerous. This variety, frozen base here, slippery base there, creates a patchwork of conditions across the continent. No single rule applies everywhere. Every region behaves differently depending on what lies beneath. This complexity is one reason why researchers often say that Antarctica doesn't just challenge explorers physically, it challenges them in terms of planning. It's not a place where you can set a route and stick to it without adjustment. It demands flexibility because it keeps changing. And that constant movement is part of why certain areas remain untouched. Even if you could reach them one year, the path might be gone the next. A safe zone could become unstable. A smooth plateau could fracture. A hidden crevasse could widen into something no one can cross. Some of the most inaccessible areas of Antarctica are located over ice features that behave unpredictably because of these internal movements. There are regions where the ice bends around buried mountains. These bending motions create stress zones where cracks are more likely. There are places where the ice funnels into narrow passageways between ridges, increasing its speed and forming deep crevasses that twist like giant frozen scars. And there are areas where the ice thins or thickens depending on long-term climate patterns, changing the entire layout of the surface. Add to this the fact that Antarctica isn't just influenced by its own internal forces but also by the surrounding oceans and atmosphere, and the picture becomes even more complicated. Warm currents can erode the underside of ice shelves, causing the ice above to weaken. Winds can carry snow across vast distances and redistribute it unevenly. Storms can reshape the surface in days, and beneath the ice, shifts in water flow can alter the conditions at the base of the sheet. Standing on this continent, it becomes clear that you're not dealing with a structure that has settled into its final form. You're standing on something that is still in the process of becoming. And because of that, the ice behaves less like a permanent surface and more like a slow-moving, unpredictable force. One that doesn't negotiate with human plans or equipment. This moving ice has enormous consequences for the idea of exploring the most remote regions of Antarctica. Even if new technology made it possible to land safely on certain parts, the ice could shift beneath the machinery hours or days later. Crevasses could open unexpectedly. A previously stable area could become unstable without warning. The surface could tilt or collapse, and the deeper cracks beneath the snow could rearrange themselves in ways that create new hazards. All of this contributes to a kind of unavoidable truth. The movement of the Antarctic ice makes complete exploration unlikely. There will always be areas too unstable to cross, too risky to approach, or too unpredictable to map with precision. These areas won't just be difficult, they'll be unimaginable to reach safely. And yet, even though these challenges prevent us from physically reaching every part of the continent, they also reveal something important. They show that Antarctica is alive in a way that most landscapes aren't. Not alive with plants or forests or bustling wildlife, but alive with motion. Alive with forces that operate independently of human presence. Alive with a stability that exists precisely because it moves at its own pace. This sense of motion leads naturally to the next part of our journey, where we begin to uncover what lies beneath the ice itself, landscapes hidden for millions of years, untouched by air or sunlight, shaped entirely by this slow-moving force above them. Let's take a step toward what the ice has been hiding all this time. Once you begin to understand how the ice shifts across Antarctica, it becomes easier to imagine how the surface can hide almost anything beneath it. But even knowing that, it's still surprising to learn that some of the continent's most dramatic landscapes aren't visible at all. They're sealed away under ice so thick and so old that entire mountain ranges have been swallowed preserved and kept out of reach. If you stood on the surface above them, you'd have no clue that jagged peaks rise thousands of meters below your feet. The world feels flat and unbroken up there. In reality, the terrain beneath the ice is anything but. People often imagine Antarctica as a simple bowl of ice, something smooth and uniform, but the bedrock beneath it tells a completely different story. It's uneven, rugged, and full of features that look more like something you'd expect in the Rockies or the Alps than at the bottom of the world. Long before ice settled onto the continent, it had valleys, plateaus, mountain chains, and ridges shaped by ancient tectonic forces. Then the climate shifted over millions of years, temperatures dropped, and snow began to accumulate layer upon layer until the original landscape vanished under ice sheets kilometers thick. Some of the most astonishing of these hidden features are the Gambutsev Mountains, often described as a mountain range as tall as the Alps and as large as the European continent. The peaks rise sharply beneath the ice, forming ridges and valleys that haven't seen open air in millions of years. They were first detected in the mid-20th century through seismic studies, not by sight. Scientists discovered them by sending vibrations into the ice and measuring how the echoes bounce back. It was a bit like tapping on a wall and realizing there's a whole room on the other side. The readings didn't match what anyone expected. Instead of flat ground or gentle slopes, the data revealed tall peaks and deep valleys hidden below a dense layer of ice. These mountains raise countless questions. How did they form? How have they stayed preserved for so long? And what might be sitting on their slopes, untouched since long before humans existed? The ice acts as both a barrier and a protective shell. Whatever lies beneath is shielded from erosion, weather, and the usual forces that shape exposed landscapes. It's like a geological time capsule sealed under pressure and frozen silence. The remoteness and the sheer thickness of the ice make it almost impossible to study these mountains directly. You can't land equipment there. You can't dig down easily without introducing contamination or risking collapse. Even the most advanced drills might not survive the conditions. And even if a hole could be drilled, the ice above is constantly moving, slowly closing any gap created. Machines can get stuck. Tunnels can refill. The entire structure acts like something that doesn't want to be opened. Other mountain ranges lie buried as well, some partially mapped, others only hinted at through radar scans. There are peaks that rise sharply beneath the ice sheet, shaping the flow of the ice around them. These peaks force the ice upward, forming domes and ridges on the surface that give small clues about what lies below. But the clues are subtle. The surface disguises much of the dramatic structure underneath. One striking example of this hidden terrain is the Ellsworth Mountains, which include some of the highest peaks in Antarctica. Parts of them rise above the ice, forming jagged ridges that loom over the interior, but much of the range is buried. These mountains stretch across hundreds of kilometres, and yet only their tallest sections break through into sunlight. Everything else, steep cliffs, deep valleys, and countless geological features remain sealed away. The exposed peaks give only the faintest idea of the massive structure they are attached to. This buried world isn't just about mountains. There are also canyons so deep and long that they rival the Grand Canyon. One of them, the Farina Rift, lies hidden under ice in West Antarctica. Radar studies suggest it stretches for hundreds of kilometres. Another, beneath Princess Elizabeth Land, may be even larger. These canyons shape the flow of the ice above them, channeling rivers of frozen mass in directions that look strange from the air. But the full shape of these features can't be seen directly. The ice covers everything, like a curtain that will never fully lift. Something similar happens with the basins scattered across Antarctica. Some of them reach depths far below sea level, yet the ice above makes them look flat and unremarkable. One such basin, the Bentley Subglacial Trench, is one of the lowest points on Earth not covered by an ocean, dropping more than 2 kilometres below sea level. You could stand on the ice above it and have no sense whatsoever of the vast emptiness beneath your feet. The ground there is so deep that if the ice weren't present, it would form a valley deeper than almost anything else on the planet. But instead of a dramatic descent, there's only a smooth frozen plain. These hidden landscapes are partly responsible for the mystery surrounding Antarctica. They make the continent unpredictable. The flow of the ice depends on the shape of the land beneath it, and because the land structure is so irregular, the ice moves in unusual patterns. Ice streams carve paths along buried valleys. Glaciers accumulate in depressions that would otherwise be invisible. Ridges redirect movement like underwater mountains diverting ocean currents. And while scientists can model some of this behaviour, they can't perfectly predict it. This unpredictability is one reason some regions remain unreachable. If you can't be certain whether the land beneath the ice slopes sharply downward or rises abruptly, planning a route becomes nearly impossible. You may think you're crossing a stable plain, only to discover that the bedrock below drops suddenly, changing the pressure in the ice and creating dangerous cracks. You may assume a region is safe based on radar data, only to find that the data missed a crevasse field hidden by snowdrifts. The buried mountains and valleys distort the surface in subtle ways, leading to situations that no equipment can safely navigate. Beyond the physical challenges, these mountains complicate scientific questions as well. Because they're sealed under ice, they hold clues about Earth's climate millions of years ago. They might contain evidence of ancient rivers, forests, or ecosystems that existed before Antarctica froze, but reaching them would require drilling through ice that has been untouched for ages, risking contamination or irreversible change to environments that have remained stable far longer than any recorded human history. Even the mere act of drilling is complicated by the ice's movement. Suppose scientists wanted to place a drill over a particular mountain ridge deep below. They'd have to ensure that the drill stayed aligned for months or years. But the ice above might shift by meters during that time. If the equipment moved even slightly, it could break. If the hole warped, it could become unusable. And if anything went wrong, the machinery might be lost forever, swallowed by the ice. Another reason these buried landscapes remain beyond reach is temperature. Deep in the interior of the continent, temperatures stay low enough to challenge even the best technology. Metal becomes brittle, batteries die quickly, fluids freeze, and the deeper the drill goes, the greater the risk that the ice will close around it. Working in such extreme conditions means everything has to be built to withstand not just cold, but pressure, weight, and movement. Even small errors can lead to equipment failures that are impossible to fix once the machinery is swallowed by snow and ice. The buried mountains also create zones where the ice is extraordinarily thick. Some regions reach depths of more than 4 kilometers from surface to bedrock. The pressure at these depths is immense. It compresses everything, making the ice behave differently than it does near the surface. Under these conditions, the ice can deform in unexpected ways. Drilling through it becomes not just hard, but risky. No one wants to bore a hole only to have it collapse or close faster than it can be maintained. There's something unusual about trying to study mountains you can never see. The closest anyone can get is through indirect methods, radar scans, seismic readings, satellite observations, but these tools have limitations. Radar waves can scatter as they pass through the ice. Seismic vibrations can produce ambiguous echoes. Snow on the surface can distort signals. Even satellites, despite their precision, can only provide certain types of data. They can't show the exact shape of every peak and valley. They can't reveal the details of rock formations. They can't replace what direct observation would offer. This lack of visibility is part of what makes Antarctica feel different from every other continent. Elsewhere, mountains define landscapes. They create boundaries, influence weather, and shape ecosystems. People climb them, name them, photograph them. But in Antarctica, huge mountain ranges exist without any human connection at all. No one has stood on most of these peaks. No one has walked through their valleys. No one has seen the sun cast shadows across their slopes. They might as well be from another planet for all the access we have to them. Standing on the ice above these mountains creates a strange sense of disconnection. You're aware that something enormous is nearby but completely inaccessible. It's like being in a building with floors you can't reach. You know they're there, but the doors are locked and the stairwell doesn't exist. The mountains remain in darkness, miles below, unaffected by the life happening above them. And strangely enough, this hidden nature is part of why certain areas may never be explored. Even if someday technology allows us to reach deeper beneath the ice without harm, the question remains, should we uncover what has remained untouched for so long? Some researchers argue that the buried landscapes contain ecosystems or conditions that haven't changed in millions of years. Disturbing them could mean losing information that only exists because they've been sealed away. Others worry about contamination. A single foreign microbe could alter an isolated environment permanently. There's also the challenge of scale. The mountains are vast. Even if we managed to sample one location, it would represent only a tiny piece of the whole. It's unlikely that we could ever fully explore the entire system without disrupting large sections of the ice sheet. And because the ice itself is so essential to global climate patterns, disturbing it could have unpredictable consequences. So the mountains remain in darkness, not because people aren't interested, but because reaching them might cause more problems than it solves. At the same time, their existence shapes the behaviour of the entire continent. The flow of ice, the formation of crevasses, the movement of glaciers, they're all influenced by these hidden giants. Understanding them will always be important, but understanding them from a respectful distance might be the only way forward. And as we move from these unseen mountains into the broader hidden world beneath the ice, another type of environment emerges, one equally mysterious but shaped by water rather than rock. These are the lakes that never see the sky, sealed away in their own isolated existence. Their story stretches beneath the frozen surface and leads us deeper into a side of Antarctica more enigmatic than any ridge or peak. Let's drift toward that quiet, unseen water next. Beneath the ice that hides the mountains and valleys of Antarctica, there is another world entirely. It doesn't look like anything on the surface. It doesn't move like the slow ice above it or rise like buried peaks. It exists in its own quiet, sealed-off way. These are the lakes that never see the sky. Bodies of water trapped beneath kilometres of ice, insulated from sunlight, storms, wind and seasons. They sit in silence, untouched by anything on the surface, holding water that may not have mixed with the outside world for millions of years. It's hard to imagine a lake without air or warmth, or the changing reflections of daylight. Most of us think of lakes as places with ripples and shorelines, insects buzzing nearby, maybe a breeze moving across the water. But the lakes under Antarctica are nothing like that. They're sealed beneath ice so thick you could stack more than 30 Eiffel Towers on top of one another and still not reach open air. And yet, despite the crushing weight and the permanent darkness, these lakes exist in liquid form. The first question people often ask is simple. How can there be liquid water under so much ice? The answer lies in a combination of pressure, insulation and geothermal heat. Ice is a good insulator. Even in the coldest parts of the continent, the ice traps heat coming from the Earth's interior. It's not a lot of heat, nowhere near what would warm a room or melt ice in any dramatic way, but it's enough to keep the temperature at the ice bedrock boundary close to the melting point. Add the enormous pressure from the weight of the ice above and the freezing point of water drops. Under these conditions, water can stay liquid even in temperatures well below what we normally think of as freezing. That means the lakes beneath Antarctica aren't shallow pools. Some are enormous. One of the largest, Lake Vostok, is roughly the size of Lake Ontario and hundreds of meters deep. It has been buried under ice for at least 15 million years, completely isolated from the atmosphere. No sunlight, no wind, no seasonal cycles, no direct contact with life from the surface. If you could look at it directly, not through radar scans or indirect measurements, but with your own eyes, you'd see a body of water unlike anything else on Earth. But of course no one has ever seen it directly. That's part of the challenge. These lakes are hidden so far below the surface that reaching them requires drilling through layers of ice that could collapse or contaminate the water. Even the idea of drilling is complicated. If you drill with equipment that uses certain fluids, those fluids could enter the lake and disrupt conditions that have remained unchanged for millions of years. If you drill too quickly, heat from the drill could melt the surrounding ice and change the lake's chemistry. Even lowering instruments into the water risks introducing microbes from the surface. What you bring with you could be more damaging than anything you intend to study. It's this risk of altering something that has remained untouched for longer than human civilization has existed that makes many scientists cautious about exploring these lakes directly. They want to understand what's there, but they also want to preserve it, and that balance is delicate. Some attempts to access subglacial lakes have succeeded, though cautiously. Lake Whillans, for example, was reached using a clean drilling system designed to minimise contamination. Samples collected from it revealed microscopic life adapted to extreme conditions. These organisms survive without sunlight, without fresh nutrients, and without the typical energy sources found on the surface. Instead, they rely on minerals, chemical reactions, and the slow trickle of water beneath the ice. This discovery raises countless questions. If life can survive in a dark, sealed lake beneath Antarctic ice, what does that say about the possibilities for life in other isolated environments? Could similar organisms exist in ice-covered oceans on moons like Europa or Enceladus? Could ancient life have evolved in places where sunlight never reached? And if life exists in the deep subglacial lakes of Antarctica, how long has it been there? Could these ecosystems represent ancient branches of life that split from the rest of Earth's biosphere long ago? Even asking these questions highlights the importance of approaching these environments carefully. A contaminated lake won't just lose its value for research, it could lose something even more important, its authenticity. It would no longer be a preserved window into ancient Earth. It would become a mixture of old and new, making it impossible to tell what was originally there. Other lakes remain entirely untouched, not because no one is curious about them, but because reaching them safely has never been feasible. Some sit beneath ice that shifts too quickly. Others lie under areas where crevasse fields make setting up drilling equipment nearly impossible. Some have ice so thick that even the most powerful drills we have today would take years to reach them. And even if someone found a way, maintaining a clean, safe connection long enough to collect samples would be extremely difficult. The lakes also vary widely in shape and size. Some are small pockets of water that fill depressions in the bedrock. Others stretch across hundreds of kilometres. Some appear to be stable, holding water that has remained in place for ages. Others drain periodically, sending water rushing beneath the ice toward the coast. These draining events can happen suddenly and silently, reshaping the flow of the ice above. When a lake drains, the ice surface can drop slightly, revealing clues to researchers watching from satellites. Then, over months or years, the lake slowly refills. This process repeats, forming a cycle hidden deep below. It's hard to describe how foreign these lakes feel when you consider them closely. They don't have waves or tides. They don't freeze and thaw with the seasons. They don't interact with weather or storms. They sit in their own isolated state, shaped by pressure, heat, and time rather than the rhythms we associate with water. They have no sky, no surface reflections, and no wind. They're worlds unto themselves. Because of this isolation, scientists see subglacial lakes as natural laboratories for studying how life might survive in extreme environments. They offer a glimpse into conditions that might resemble early Earth, before sunlight reached the oceans or before the atmosphere took its modern form. They also provide clues about how water moves beneath the ice sheet, which in turn influences the stability of the ice above. The lakes aren't just interesting scientifically, they also play a practical role in shaping Antarctica's behaviour. Water beneath the ice can make the ice sheet slide more easily. When a lake drains, it can speed up the flow of ice streams downstream. When a lake fills, it can change pressure patterns across large regions. These small changes can influence ice movement over hundreds of kilometres. In this way, the lakes are part of the continent's internal machinery. They help decide which areas remain stable and which become too unpredictable to explore. There's something strange and humbling about knowing that these lakes exist just beneath your feet while giving no hint of their presence. You could stand directly above one of them and see nothing but an endless white field. You wouldn't hear anything, you wouldn't feel anything, but below, in pressure and darkness, an entire world exists, separated from yours by a thickness of ice that has been accumulating for millions of years. The isolation of these lakes is one reason certain regions of Antarctica remain unexplored. You can't place heavy equipment in areas where the ice might collapse into a void. You can't drill freely without risking contamination. You can't send people across these zones without understanding where the ice is strongest or weakest. And because the lakes lie in places where the ice is thickest and most unpredictable, they naturally lie in regions that remain untouched. Even the simple act of mapping these lakes is complicated. Radar can detect water because it reflects signals differently than ice. But distinguishing one lake from another, determining whether water is flowing, deciding how deep each lake is, this requires careful interpretation. Some lakes appear to be shallow, others seem deep, some are isolated, others seem part of a connected network. The picture is never fully clear. Every new dataset adds detail but also raises new questions. There's also the matter of pressure. The water in these lakes exists under conditions far different from anything at the surface. If drilled improperly, the pressure difference between the lake and the drilling equipment could cause the water to rush upward, freezing the equipment or altering the lake's chemistry. Planning for such extremes requires precision far beyond normal engineering challenges. In the end, the existence of these lakes reflects something bigger about Antarctica. The continent isn't just cold, it isn't just remote. It's structured in layers of mystery, each one harder to access than the last. The buried mountains are one layer, the ice sheet's movement is another, and the subglacial lakes form yet another layer, one that sits quietly in darkness, untouched and unreachable. Imagining what lies in these lakes is tempting. What might be living there? What shapes might the water take? What sediments lie at the bottom, recording stories older than our species? But for all the temptation, there's a sense of responsibility too. Opening these lakes too freely could destroy them before we even understand what they are. And because of that, many of them remain undisturbed, perhaps indefinitely. This idea, that whole environments exist beneath Antarctica that humans may never witness firsthand, adds another piece to the puzzle of why some parts of the continent may remain unexplored. It isn't only about physical danger or distance, it's about preserving what has endured untouched for millions of years. And beneath these dark lakes lies yet another challenge, one that affects not only life below the ice, but the very possibility of exploration anywhere near them. That challenge is the cold that dominates the continent, a cold so intense that it shapes everything that exists there, from the ice itself to the equipment that tries to measure it. We can move toward that next, where temperature becomes the deciding force behind what is reachable and what remains out of reach. The deeper you travel into Antarctica, the more the temperature becomes something you don't just notice, but something that takes control of everything around you. It isn't like cold weather anywhere else. It isn't the kind of chill that sinks through a coat or settles into your fingers. This cold changes the rules of what's possible. It decides how machines work, how people move, how the ice behaves, and how far anyone can go. It shapes the very idea of exploration, setting limits that don't yield no matter how advanced our technology becomes. Antarctica holds the record for the coldest temperature ever measured on Earth. A reading from satellite data placed a spot on the East Antarctic Plateau at around 93 degrees Celsius, colder than dry ice, colder than anything you could safely touch without it burning you in reverse. Even on a warmer day in the interior, temperatures can stay well below 40 degrees. In some places, the air is so dry that moisture from your breath freezes instantly, forming a cloud of tiny crystals that drift downward like dust. At these temperatures, exposed skin can freeze in less than a minute. Metal becomes brittle, plastics crack, lubricants thicken, Batteries drain so quickly that some devices shut down before you've even had time to use them. This cold doesn't just make exploration uncomfortable, it stops certain types of exploration entirely. Machines simply don't behave the way they should. Vehicles that function well in Arctic regions fail when exposed to the extreme temperatures of the Antarctic interior. Fuel thickens, engine parts seize, rubber loses flexibility. Even the process of starting a motor becomes a struggle, because the cold robs energy faster than it can be generated. Engineers have spent years designing specialized equipment for polar research stations, yet even these machines require constant heating, shields, and modifications to survive. The cold affects people just as strongly. Human bodies aren't built to withstand these temperatures, even with multiple layers of specialized clothing. Frostbite becomes a risk within minutes. Your eyelashes can freeze together. The moisture in your nose can crystallize. Breathing deeply becomes painful because the air feels sharp entering your lungs. Movements slow down. Muscles stiffen. Your brain works harder to stay alert. And the longer you stay in the cold, the more your body struggles to maintain its temperature. Even hydration becomes difficult, because every drop of water has to be kept warm to avoid freezing. Inside research stations, the temperature feels manageable only because heaters run constantly. Step outside, though, and everything changes instantly. Researchers often describe opening the station door as stepping into a completely different world. The air feels heavier. The cold hits so sharply that it can take your breath away. And that's on days when the wind is gentle. Add wind, and the conditions move from harsh to dangerous. Wind chill in Antarctica can push temperatures to levels that would kill a person quickly without proper clothing. The wind doesn't just feel cold, it cuts through layers. It removes heat from the body faster than you can produce it. It erases footprints and snow tracks in seconds. It can even carry away loose items or push people off balance. In the interior of the continent, winds can reach speeds that make standing still a challenge. Combine that with temperatures below 60 degrees Celsius, and you have an environment where even basic tasks, tightening a strap, adjusting a glove, checking equipment, become complicated. Because of this, many areas of Antarctica are effectively unreachable during most of the year. There are places where the cold is so persistent and so extreme that teams cannot safely work there, even briefly. Flights to the interior must be carefully scheduled and often cancelled because fuel or hydraulic systems cannot operate at the temperatures expected upon landing. Helicopters struggle in the thin, freezing air. Ground vehicles cannot risk being stranded in zones where rescue would be impossible. The cold also influences the ice itself. When temperatures reach extreme lows, the ice becomes harder and more brittle. It doesn't behave like a solid sheet. It cracks with sharp, sudden noise. It can fracture under pressure, creating new crevasses without warning. These crevasses can appear in places previously considered stable, making travel dangerous even in areas that seemed predictable the year before. The colder the ice becomes, the more unpredictable it gets. This unpredictability contributes to the difficulty of exploring the most remote regions. You could plan for the terrain as it appears on satellite data, only to arrive and find that the surface has shifted, split, or changed texture. The cold amplifies the natural motion of the ice by making it more rigid. When it bends or moves under pressure, it does so abruptly rather than gradually. This leads to sudden changes that equipment can't always detect. In many ways, the cold becomes a barrier thicker than the ice itself. Even if you could drill through kilometres of ice, cross crevasse fields safely, and navigate shifting terrain, you would still face the problem of keeping people and equipment functioning in temperatures that strain the limits of engineering. Some regions remain unexplored simply because no current technology can stay operational there long enough to gather useful data. Tools that work flawlessly in other climates malfunction instantly in the deep interior. Electronic equipment faces unique challenges. LCD screens freeze, wires stiffen, sensors can produce inaccurate readings because the cold interferes with calibration. Batteries must be kept warm at all times, which means equipment often needs to be insulated or heated. Some researchers carry batteries close to their bodies so the warmth keeps them functional, but this only works for small devices. Larger instruments require dedicated heating units, which adds weight and complexity to missions that are already challenging. Even the best scientific instruments have limits. At extremely low temperatures, some types of signals become faint or distorted. Radar waves, for example, travel differently when the ice is extremely cold. The ice becomes harder and denser, affecting how deep signals can penetrate. This makes it harder to identify features below the surface. In some regions, the cold prevents researchers from getting accurate readings at all, leaving the landscape beneath the ice poorly understood. But perhaps the most subtle effect of the cold is on time itself. Not literally, of course, but in the way that events unfold. Everything slows down. Working outside takes longer. Setting up equipment takes longer. Travelling between research sites takes longer. Mechanical failures become more common. Brakes are needed more often to warm up. Repairs are more complicated because fingers lose dexterity in the cold. People move carefully to avoid accidents that could become life-threatening. A simple mistake, dropping a tool, failing to secure a piece of equipment, can become a serious situation if recovery requires stepping into the cold longer than planned. This slowing of activity means that large-scale missions become harder to complete. If a team needs to reach a remote region that requires several days of travel, extreme cold can delay progress until the schedule becomes unrealistic. Supplies might run low, weather windows might close, the return trip might become impossible. Because of this, many ambitious exploration proposals never leave the planning stage. The cold imposes a time cost that cannot always be paid. Even when conditions are relatively stable, the cold can create psychological challenges. Extended exposure to extreme cold can make people feel isolated or fatigued. The constant effort to stay warm, stay alert, and stay safe wears down even the most experienced researchers. When the cold becomes the dominant feature of every moment, the mind shifts into a careful, cautious state. This can be mentally exhausting, especially for teams working far from any base. It adds another layer of difficulty to exploring regions already known for their risks. It's important to remember that Antarctica isn't simply cold. It is the coldest place on Earth by a wide margin. Other places have severe winters, harsh winds, or nights that last for months, but no other location combines such low temperatures with such dryness, such wind speeds, and such elevation. Much of the continent sits high above sea level, on a plateau formed by the weight of the ice. Higher altitude means thinner air and colder conditions. The interior's dryness also intensifies the cold, because there is almost no moisture in the air to hold heat. In some places, the cold is so sharp and dry that snow doesn't melt or compact. It simply accumulates layer after layer without changing texture. When you put all of this together, the dryness, the altitude, the wind, the ice, and the temperature, you get a region where normal rules of movement and survival don't apply. It's not just inhospitable, it's actively resistant to human presence. The cold doesn't merely discourage exploration, it prevents large sections of the continent from being reached at all. This is part of why certain regions of Antarctica remain untouched. Not because no one wants to explore them, and not because they lack scientific value, but because reaching them would involve exposing people and equipment to conditions that exceed what is currently possible. Even if someone were determined to reach these places, the risk would outweigh the reward. A failed rescue attempt in such an environment would be nearly impossible. Even experienced teams must stay within zones where help could eventually reach them. And even if technology improves in the future, the cold will remain a deciding factor. Some areas are so consistently cold that no seasonal variation provides a safe window. Others experience spikes of dangerous cold that appear without warning. Planning around these fluctuations would require precision far beyond what is currently achievable. All of this creates a reality where Antarctica doesn't just test the limits of exploration, it defines them. The cold is both a physical barrier and an environmental authority. It decides where people can go, where machines can operate, and where data can be collected. It slows progress, introduces danger, and creates boundaries that no map can fully convey. And as powerful as the cold is, it isn't the only force shaping which regions remain beyond reach. There is another factor that merges with the cold, with the moving ice, with the buried landscapes, and with the hidden lakes. This force travels across the continent in ways just as relentless as the ice itself. Winds strong enough to reshape the surface, erase tracks, and create landscapes that shift hour by hour. That is where we head next, into the air that never sits still, and the winds that define the outer edges of what exploration can accomplish. If the cold in Antarctica sets the boundaries for what can survive and what cannot, the wind is what enforces those boundaries. It moves across the continent with a consistency and strength found nowhere else on Earth, shaping the surface in ways that few people ever witness directly. And unlike the ice, which shifts slowly, or the hidden lakes and mountains which remain locked away in darkness, the wind is always active. It never settles. It never rests. It defines the rhythm of Antarctica in motion, sweeping across thousands of kilometres with a force that can erase footprints, flatten equipment, and change the shape of the landscape within hours. For anyone trying to understand why certain regions of Antarctica remain unreachable, the wind becomes a central part of the story. It isn't just a strong breeze or a severe storm, it's a constant presence that influences every aspect of exploration. Even on days when the sky is clear and visibility seems perfect, the wind has a way of reminding you who is in control. These winds are known as katabatic winds, created when cold, dense air from the interior flows downward toward the coast, under the pull of gravity. Because Antarctica's interior sits high on a plateau, the air up there becomes heavier as it cools, then slides down the steep slopes with steady acceleration. This creates winds that can reach speeds of more than 200 kilometers per hour. In some regions, gusts stronger than hurricane-force winds can blow for hours, days, or even weeks at a time. The result is an environment where the air itself becomes a barrier. Imagine standing outside and hearing nothing but the roar of movement around you. The wind pushes against your body with enough pressure to make walking difficult. Snow, even tiny crystals, strikes your face hard enough to sting. Visibility can shift from clear to nearly zero as the wind picks up loose snow and sends it swirling into the air. There's no shelter in the vast open spaces. You can't hide behind trees or buildings. Even large vehicles struggle to stay steady. Every motion becomes deliberate, cautious, and slow. Because the wind blows so consistently, it sculpts the snow into shapes that don't appear in other parts of the world. Long, low ridges known as sastrugi form across the surface, shaped by the steady direction of the wind. These ridges can be small, or can grow so tall and sharp that they resemble frozen waves. They present real challenges for travel. Vehicles bounce and slide across these uneven surfaces, and sleds carrying equipment catch on the ridges and tip over. The terrain becomes unpredictable, not because the land changes, but because the snow on top is constantly rearranged. In some parts of Antarctica, winds sweep across the surface with such force that they carve the snow away entirely, exposing bare ice. This ice is polished until it becomes almost mirror smooth. Walking on it without spikes or crampons would be nearly impossible. Sliding across it in a vehicle would be even more dangerous. These windswept areas can stretch across large distances. They aren't marked on maps in the way mountains or hills are, because they shift from year to year as storms reshape them. Travelling through them requires constant assessment, slowing progress, or halting it entirely. The wind also removes snow from some areas and piles it in others. Drifts can accumulate several meters deep in a matter of hours. A structure left on the surface can be buried overnight. Equipment that was reachable yesterday may be hidden today. Camps must be constantly monitored to prevent them from being covered. And because the wind doesn't move in neat patterns, drifts can form in unexpected places. Even experienced researchers can be surprised to wake up and find their vehicles surrounded by snowbanks that weren't there before. This constant reshaping makes navigation difficult. Satellite images may show a relatively smooth region, but the wind can alter that surface faster than any satellite can update its data. A planned route might be safe one week and impassable the next. And because the surface is rarely uniform, travelling long distances becomes physically demanding. The wind slows everyone down, saps energy, and forces teams to spend more time outdoors than intended, increasing the risk of frostbite, equipment failure, or accidents. The wind doesn't stop with reshaping snow, it affects the ice below as well. Over time, persistent winds can push snow into crevasse fields, covering gaps with thin layers that hide the danger beneath. These snow bridges can look solid but collapse under weight. Anyone travelling across wind-affected areas must constantly probe the ground, testing each step or each metre of movement. Vehicles may use radar systems to detect hidden crevasses, but even these tools are imperfect. The wind disguises the signals, scattering the reflections and making interpretation more difficult. Storms are a separate challenge entirely. In many places, Antarctic storms don't bring heavy snowfall. Instead, they bring heavy wind. They lift existing snow into the air, creating whiteout conditions where the horizon vanishes. Researchers describe these storms as disorienting. You lose any sense of direction. Sometimes you can't even see the ground beneath your feet. Sound becomes muffled, taking on the hollow tone of a world made entirely of wind. People must navigate by following ropes tied between buildings, or by staying indoors until the storm passes. These storms can arrive with little warning. Weather predictions in Antarctica are more difficult because the continent's conditions differ dramatically from those elsewhere. Incoming weather systems interact with the cold interior in unpredictable ways. Small changes in temperature or pressure can turn a mild breeze into a dangerous event. When storms arrive unexpectedly, they can trap expedition teams in their tents or vehicles. Travel becomes impossible. Work halts. Supplies must last until conditions improve. Because of this unpredictability, many regions of Antarctica remain unexplored simply because no one can guarantee that the journey there will be safe. Even with strong equipment and careful planning, an unexpected storm can delay or end an expedition. And in areas far from stations or supply drops, getting caught in a storm could be life-threatening. Wind speeds are too high for aircraft to land safely. Ground rescue teams cannot travel. Communications may struggle. Everything depends on waiting for the wind to relent, which sometimes takes much longer than anyone would hope. The effect of these winds extends beyond human travel. They also shape the continent's climate system. The strong winds circulating around the continent create a kind of barrier in the atmosphere. This barrier traps cold air over Antarctica and keeps warmer air from entering. This helps maintain the extreme temperatures that make exploration difficult. The winds, in a sense, help protect the continent from significant warming, but they also help keep it isolated. That isolation is felt not just in terms of climate, but also in terms of access. Then there are the areas where the wind interacts with the ice shelves. Strong winds can push sea ice away from the coast, opening gaps where the water below is exposed. These open water regions can fuel further changes in weather and ice formation. In some places, the winds create polynyas, patches of open water surrounded by ice, that can alter local ecosystems. In other places, the winds help push cold air downward, strengthening the katabatic currents that make travel inland even harder. This layering of effects, surface shaping, visibility reduction, equipment strain, and unpredictable storms, creates zones across the continent that are nearly impossible to reach. Some of these zones sit near the coast, others lie deep in the interior. Many have never been crossed by humans, not because they lack interest or scientific value, but because the wind makes reaching them too dangerous. The wind also plays a role in preserving certain untouched regions. By constantly reshaping the surface, it removes signs of previous visitors. It erases footprints, tyre tracks, and even markers. It returns the landscape to a state that appears never touched. There's something striking about this. In most parts of the world, traces of exploration remain for years or decades. But in Antarctica, the wind ensures that the surface resets quickly. It's as if the landscape insists on staying unchanged, regardless of what passes through. Some researchers describe these untouched regions as feeling almost otherworldly. There's a sense that the wind isn't just shaping the snow, but also holding the environment at a distance. Even approaching these areas can feel like pushing against a force that isn't meant to be crossed. It's not mystical or symbolic. It's simply the physical reality of a continent defined by conditions so extreme that they act as natural boundaries. In practical terms, the wind affects the logistics of exploring remote regions more than almost anything else. For example, landing an aircraft in Antarctica requires long, flat surfaces free of large drifts. But wind constantly reshapes these surfaces. An area considered safe for landing one season might become dangerous the next if snow builds up into ridges. In other areas, the wind exposes hard blue ice that is too slippery or uneven for planes to land safely. Even areas that look perfect for landing can become hazardous if crosswinds push aircraft off course. Because of this, many remote parts of Antarctica remain without landing sites. And without landing sites, no expedition can reach them without massive ground effort that the wind complicates even further. Driving across the interior for hundreds of kilometres in high winds isn't just slow, it can be nearly impossible. The constant stress on engines, the risk of getting stuck in drifts, the danger of losing visibility, and the sheer exhaustion of moving through such conditions all build up quickly. Even drones, one of the most promising tools for remote exploration, face serious limitations. Extreme wind speeds make stable flight nearly impossible. Batteries freeze. Rotors lose power. Navigation systems struggle. In many parts of the continent, drones cannot operate for more than a few minutes, leaving entire areas unobservable from the air. So while the wind may seem like just another aspect of Antarctica's harshness, it's actually central to understanding why large portions of the continent remain unexplored. It is, in many ways, the most active force shaping which regions can be reached safely and which remain off-limits. When you take all of this together, the constant reshaping of the surface, the unpredictable storms, the strain on equipment, the dangers for travellers, and the isolation caused by atmospheric barriers, you begin to see how the wind sets the final limitations on exploration. It turns Antarctica from a cold, remote continent into a constantly shifting environment where access is never guaranteed. And yet, amid the difficulty created by these winds, there exists another world that remains even more unreachable. Not because of storms or shifting snow, but because it lies in darkness beneath the ice, inhabited by organisms adapted to conditions most life could never endure. These creatures exist far from sunlight, far from warmth, and far from human presence, and they remind us that Antarctica isn't empty. It holds life, but life that thrives in the kinds of places people may never reach. That is where the next part of our journey leads, into the quiet depths where the hidden inhabitants of Antarctica make their home. When most people imagine Antarctica, they picture a landscape that seems completely empty. A blank canvas of ice and wind, too cold for anything to survive. And on the surface, that impression feels accurate. The continent looks like a place stripped of life. There are no forests, no grasslands, no insects buzzing through the air, no plants climbing across the surface. Just snow, ice, and the distant calls of seabirds near the coast. But beneath that frozen expanse, in places untouched by sunlight or warmth for millions of years, life has found ways to exist in the unreachable dark. This kind of life doesn't resemble the thriving ecosystems seen in warmer environments. It isn't made up of bustling communities or visible animals wandering the land. Instead, it survives at scales too small to see with the naked eye, in pockets too hidden for most equipment to reach, and under conditions so extreme they seem more suited to science fiction than Earth. Yet these organisms endure. They grow, reproduce, and persist in places where nothing else can. They embody a kind of patience that matches the slow pace of Antarctica itself. To understand them, you have to picture what it means to live under kilometres of ice. There is no sunlight. Not ever. There are no seasons. The temperature stays consistently below freezing, except in narrow zones where geothermal heat warms the environment just enough for liquid water to exist. Nutrients arrive so slowly that growth happens at a glacial pace, often taking decades or centuries to show noticeable change. Pressure is intense. Water beneath the ice exists under conditions that would be hostile to most forms of life. Yet microbes, tiny, resilient, remarkably adaptable, have managed to claim these spaces as their home. Scientists know these organisms exist not by seeing them directly in most cases, but through careful sampling, indirect measurements, and occasionally rare access to subglacial environments. When researchers successfully reached Lake Whillans, for example, they found a wide variety of microbial life. These tiny communities weren't surviving on sunlight or organic matter from the surface. They were living off minerals, chemical reactions, and the slow movement of water beneath the ice. Some microbes used iron or sulfur compounds for energy. Others relied on tiny amounts of carbon carried from the bedrock. They survived in near total isolation, proving that life doesn't always require the conditions we're familiar with. These discoveries changed how scientists think about extreme environments. If life can survive in Antarctica's subglacial lakes, cut off from sunlight for millions of years, then perhaps similar forms of life could survive in other hidden places on Earth. And even more intriguingly, perhaps life could exist on icy worlds elsewhere in the solar system. Places like Europa or Enceladus suddenly seem less hypothetical in that regard. But beyond those big possibilities, these Antarctic organisms also reveal something about our own planet, that life can adapt to environments we once assumed were completely uninhabitable. But while scientists have been able to sample a few of these hidden pockets, the vast majority of Antarctica's subglacial ecosystem remains out of reach. Most lakes lie too deep beneath the ice. Many are covered by crevasse fields or unstable surfaces. Some are simply too remote. And because accessing them risks contamination, many researchers believe it's better to leave them untouched. Introducing a foreign microbe or chemical into a sealed environment could permanently change it. It would erase the very conditions that make the lake interesting in the first place. Even away from the lakes, microbial life has been found in the ice itself. Some organisms are trapped inside tiny pockets of liquid water that form when pressure causes ice to melt slightly. These pockets, known as brine channels, can exist even at temperatures far below freezing. Inside these channels, microbes survive in environments saltier than seawater, colder than most freezers, and darker than the deepest caves. They feed on whatever they can, minerals, gases, organic molecules carried by the ice. Their metabolism slows almost to a standstill, but it doesn't stop. In some cases, these microbes may be older than human civilization. They've remained dormant for long stretches of time, only becoming active when conditions allow. The ice acts as both their home and their prison. It preserves them in a kind of suspended existence, letting them endure hardships that would destroy most life. Further beneath the ice, especially in zones where the ice meets the bedrock, even stranger ecosystems may exist. The combination of pressure, liquid water, and minerals creates conditions where certain microbes can use chemical reactions to produce energy. Some rely on methane, others on ammonia or sulfur. These organisms live in environments so harsh and isolated that studying them requires incredible care. Every sample must be taken without introducing anything from the surface. Every instrument must be sterilized, heated, and cleaned repeatedly. A single error could contaminate the sample and ruin the research. This is one of the reasons so much of Antarctica's dark ecosystem remains unexplored. Access requires technology that is both precise and clean, but even the most advanced tools have limits. Drills can fail, equipment can freeze, and the ice itself moves, closing holes or distorting pathways before samples can be collected. In some places, the risk of contamination is so high that researchers agree it is safer not to drill at all. This creates large zones where microbial life may exist, but remains entirely hypothetical. Radar scans hint at pockets of water. Temperature measurements suggest possible habitats, but no one can say for sure what lives there, if anything does. These places remain as mysteries, sealed off by nature and protected by the challenges of accessing them. Of course, life in Antarctica isn't limited to the deep subsurface. Near the coastal regions and around research stations, more familiar organisms can be found. Penguins, seals, and various birds thrive in the relative warmth of the coastal environment. Microbes grow in meltwater pools during the summer months. Tiny invertebrates, such as tardigrades and nematodes, live in soil patches that thaw briefly each year. But these creatures exist in the comparatively mild environments near the edges of the continent. The deep interior, the buried lakes, and the regions beneath the ice sheet host life that is far different and far more isolated. In some sense, the organisms living in these hidden environments help define what unexplored means in Antarctica. Even if we never send a person or a drone into these places, life may be thriving there on its own terms. The ecosystem continues without human observation or interference, and because of the risks involved in reaching these environments, there's a growing perspective within the scientific community that some of these places should remain untouched. They are natural laboratories, but they are also fragile. Introducing human presence, even indirectly, could undo millions of years of isolation. Every attempt to study subglacial ecosystems has to weigh the benefits against the risks. Learning more about these organisms could advance our understanding of life on Earth and elsewhere. But altering the environment, even slightly, could erase the very conditions that make it valuable. Some lakes have been designated as protected zones for this reason. Researchers are allowed to study them indirectly, but cannot drill into them except under strict guidelines. This ensures that the environment remains intact, even if it means leaving many questions unanswered. This caution is part of why so many regions beneath the ice remain unexplored. It's not just physical inaccessibility or danger, it's also about respecting environments that have remained stable without any interference. The organisms living there have adapted to conditions that are delicate and finely balanced. Even small changes, heat from a drill, chemicals from equipment, or microbes from the surface, could alter them in ways that cannot be reversed. Another layer of complexity comes from how little we understand about the movement of water beneath the ice. Subglacial lakes can drain suddenly, sending water rushing through channels that carve new pathways. Streams can open or close. Conditions can change without warning. If life exists in these areas, it might be moving with the water, spreading across the hidden network beneath the ice sheet. Or it might remain contained within isolated pockets. The truth remains unknown because direct exploration is so limited. Despite the difficulty, the presence of life in these unreachable places shows that Antarctica is not a dead continent. It's a place where life has adapted in ways that seem almost impossible. These adaptations challenge assumptions about what is needed for survival and how ecosystems form. They remind us that life is not confined to environments familiar to us. And although most of these organisms are microscopic, their existence has significant implications. They contribute to chemical cycles beneath the ice. They influence the behavior of water and minerals. They help shape the conditions of their environments. In a subtle way, they are part of the continent's hidden machinery, working quietly in the dark. The presence of life in the unreachable regions of Antarctica also shapes the ethics of exploration. If these environments host unique ecosystems that have remained isolated for millions of years, then disturbing them becomes not just a scientific challenge, but a moral one. Some researchers argue that these ecosystems should remain untouched forever. Others believe that careful exploration can uncover valuable knowledge without causing harm. It is an ongoing debate, shaped by both scientific curiosity and ethical responsibility. This debate intersects with another layer of the continent's complexity, the sheer weight of the ice that covers it. The ice sheet is not just a barrier to exploration, it's a massive dynamic structure that influences the movement of water, the shape of the land, and the conditions in which life exists beneath its surface. Understanding this weight and the consequences of its movements is essential for understanding why so much of Antarctica remains beyond our reach. And that brings us naturally to what lies ahead, where the scale of the ice becomes as important as what it hides, and where the continent's immense mass reveals its own kind of force. Let's continue into that next, where the weight of a continent defines what humans can and cannot explore. The more you think about the ice covering Antarctica, the more its scale becomes difficult to grasp. It isn't just a layer of frozen water sitting politely on top of the land. It's a continent-sized mass with a depth, weight, and influence unlike anything else on Earth. It reshapes the bedrock beneath it. It redirects the flow of water. It presses downward with such force that entire regions of land have sunk under its load, and it moves with a slow persistence that can change the landscape over thousands of years without ever appearing to move at all. When people talk about the frozen interior of Antarctica, they often focus on the cold or the wind or the isolation, but the weight itself, the sheer physical mass of the ice, is one of the most decisive reasons some parts of the continent may remain unexplored. To understand the scale of this ice, imagine a sheet that covers an entire continent with an average thickness of more than 2 kilometres. In some places it reaches nearly 5 kilometres deep. That's deeper than the height of many mountain ranges. It's enough ice that, if melted, would raise global sea levels by many metres, and all of that weight presses down constantly on the land beneath it. The pressure is so tremendous that bedrock has been pushed far below sea level. Some of these depressions would form basins deeper than any valley on the surface if the ice were removed. This weight also explains why the ice behaves the way it does. Ice doesn't seem like something that flows, at least not in daily life. But under this kind of pressure it behaves like a very slow-moving substance. It deforms, stretches, and creeps outward. It slides along the ground in some places, while in others it sticks to the rock and creates tension. The entire structure moves not like a block, but like an enormous viscous material responding to gravity and internal pressure. We tend to think of ice as fragile or static, but under these conditions it becomes a dynamic force. For explorers or researchers trying to reach the most remote parts of Antarctica, this weight becomes a major obstacle. The ice's mass affects the surface conditions in ways that make travel difficult. Where the ice is thickest, the pressure affects temperature and creates zones where meltwater can form at the base. This meltwater lubricates the ice, making it slide more easily. Areas with basal water often move faster, creating unstable regions where crevasses open unpredictably. These zones are among the most dangerous places to cross because the surface may look completely smooth, even while the ice beneath shifts constantly. In other areas, the weight of the ice holds the base so firmly against the bedrock that no water can form. This creates regions where the ice is locked in place, producing different patterns of stress. When these rigid zones border faster-moving areas, cracks form along the boundaries. These cracks can extend deep into the ice, forming crevasses that are nearly impossible to detect from the surface. The thicker the ice, the more deeply these fractures can extend. It becomes a world built from pressures interacting with one another in ways that aren't always predictable. The weight also shapes the land beneath the ice in long-lasting ways. Because the ice is so heavy, the bedrock doesn't simply sit still under it. It bends and flexes, rising or falling slowly depending on how the ice above moves. When ice accumulates, the land sinks further. When ice retreats, the land rebounds upward, a process known as isostatic adjustment. But this adjustment is incredibly slow. In some places, the land is still rising from changes that happened thousands of years ago. These shifts influence the flow of water beneath the ice. They alter the shape of subglacial lakes. They affect where meltwater collects and how it drains. It is this interplay, ice pressing down, land reacting, water moving through channels, that creates a constantly evolving environment beneath the surface. And because most of this happens over such long timescales, humans can't witness it directly. We only see the effects through equipment readings or satellite data. But the consequences are real. In areas where the land is sinking under the weight, deep valleys form. These valleys may trap water or redirect it. In areas where the land rises, the ice above can thin, forming regions where cracks or faults are more likely. All of this contributes to the difficulty of understanding and exploring the continent. Nowhere is this complexity more evident than at the edges of the ice sheet. Here, the enormous pressure from the interior pushes ice outward toward the coast, where it flows into ice shelves that float on the ocean. These shelves act like extensions of the continental ice, forming platforms hundreds of meters thick. They are shaped both by the ice behind them and the ocean beneath them. When ice shelves remain stable, they help regulate the flow of the ice sheet. But when they weaken or collapse, the inland ice can accelerate. This creates a chain reaction that affects everything behind it. The ice shelves themselves are massive structures. Some stretch across areas larger than many countries. They form cliffs of ice that rise high above the ocean surface. They crack, bend, and carve icebergs that drift out to sea. They also hide enormous cavities beneath them where warm ocean water can flow. These cavities form because the weight of the ice depresses the shelf, making it sag into the water. As the ocean circulates beneath, it melts the ice from below. This process is difficult to measure because it requires understanding both the movement of the ice above and the currents beneath. Reaching the underside of an ice shelf is nearly impossible in most regions. The water below is hidden by a ceiling of ice hundreds of meters thick. The ice above moves constantly. The ocean currents below shift unpredictably. Equipment must survive intense pressure, darkness, freezing temperatures, and rugged surroundings. This combination of challenges has left large areas beneath the shelves unexplored. Even with modern technology, there are places no robot or instrument has managed to reach safely. Farther inland, the weight of the ice creates other types of barriers. When ice becomes thick enough, the pressure affects how it breaks. The ice can fracture in complex patterns that create vast labyrinths of crevasses. These crevasse fields can stretch for miles, hidden beneath snow that drifts over them. The weight pressing down from above creates deep cracks that spread through the ice like fault lines. These features are some of the most dangerous obstacles for ground exploration. They can appear suddenly, widen unexpectedly, or remain concealed under soft snow until a vehicle or person breaks through. The weight of the ice also affects how heat moves through the continent. Because ice is a good insulator, the warmth generated by Earth's interior becomes trapped beneath the sheet. In some areas, this leads to the formation of subglacial lakes or meltwater networks. In others, it creates zones where the ice is more likely to deform or slide. These thermal variations shape the landscape in ways that are difficult to predict. A region that appears stable might hide a warm patch beneath the ice, causing it to move faster or produce meltwater unexpectedly. All of this adds complexity to planning expeditions. If you look at Antarctica from above, it's easy to think the surface is fairly uniform, but the weight of the ice makes the surface uneven in subtle ways. Some areas sit higher because the ice beneath is pushing upward. Others sit lower because the ice is heavier or the land has sunk. These changes in elevation affect wind patterns, snow accumulation, and temperature. Over time, they help form the distinct zones that make up the continent's interior. Each zone behaves differently, influenced by the underlying weight of the ice. One of the most striking effects of the ice's weight is how it hides the land beneath. Without the ice, Antarctica would look dramatically different. It would have high mountain ranges, deep valleys, and broad plains. Some areas would be mountainous. Others would be low basins filled with lakes or rivers. But with the ice pressing down, all of this becomes hidden. The land beneath is shaped not only by ancient geological forces, but also by the weight above it. In some areas, the bedrock has been pushed so low that it lies more than a kilometre below sea level. These basins are filled with ice instead of water, forming enormous frozen reservoirs. The weight of the ice also contributes to the continent's isolation. It helps maintain the cold interior by keeping the land at high elevation. The East Antarctic Plateau, for example, sits thousands of metres above sea level because the underlying land has been lifted by the sheer mass of the ice over time. This elevation contributes to the extreme temperatures that make exploration so difficult. Without the ice, the land would sit much lower and likely be warmer. The weight, in this sense, reinforces the conditions that make the continent so challenging. All of these factors combine to create regions that are physically unreachable. It isn't simply that the ice is thick, it's that the thickness changes the character of everything around it. Travel becomes difficult. Equipment becomes unreliable. The ground beneath becomes unstable. Any attempt to reach certain areas must contend with pressures that reshape the environment constantly. Even the best technology struggles in places where the weight of the ice changes the rules from moment to moment. And yet, despite all of this complexity, the weight of the ice plays a stabilizing role in some parts of the continent. In areas where the ice is thick and cold enough, the surface becomes relatively smooth. These regions can appear deceptively safe, with flat plains stretching as far as the eye can see. But beneath that surface lies the same massive pressure and the same unpredictable forces. Exploration in these areas still requires caution because the stability on the surface doesn't reflect stability below. This sense of hidden forces, of massive weight shaping the land while remaining invisible to those above, adds another layer to the challenge of exploring Antarctica fully. Even if humans could navigate the surface, drilling into the ice remains a significant challenge. Maintaining a borehole in ice under such pressure is extremely difficult. The hole can close as the ice flows around it. Instruments can be crushed or trapped. Even sampling the deepest layers of the ice requires careful engineering to prevent the structure from collapsing. This is one reason some scientific goals remain out of reach. The weight itself limits what can be studied. This enormous mass also influences global systems. It affects sea levels, climate patterns, and ocean circulation. Changes in the ice sheet's weight can alter the tilt of the Earth's crust, affecting geological processes. All of this is a reminder that the ice doesn't just sit on Antarctica, it is Antarctica in many ways, shaping the continent at every level, from surface to bedrock. Understanding how this weight governs the environment leads naturally into the next challenge. Even if we found ways to withstand the cold, the wind, the moving ice, the hidden lakes, and the buried mountains, we would still face the problem of technology's limits. Machines are finite. Tools break, systems fail, and Antarctica is a place where the environment pushes every piece of technology closer to its breaking point. That's where we go next, into the question of why even our best inventions struggle in the most remote corners of this continent. Even after understanding the cold, the wind, the buried mountains, the moving ice, the unreachable lakes, and the sheer weight pressing down on the continent, there is still another problem that keeps Antarctica's most remote corners beyond reach. It's one thing to imagine people crossing those regions on foot or with sleds. It's another to imagine machines trying to survive there. And for all the progress made in engineering, all the breakthroughs in robotics, all the durability built into modern science equipment, Antarctica remains one of the only places on Earth where technology routinely fails, not because it's poorly designed, but because the environment overwhelms it in ways engineers can barely anticipate. Every machine sent into Antarctica faces the same basic threats: extreme cold, shifting surfaces, unpredictable winds, low humidity, mechanical stress, and the constant possibility of ice damage. But these threats don't act alone. They interact. They stack. They compound each other until even the most advanced tools reach their limits. What might work perfectly in a desert, on a mountain, in space or under the ocean, can break in minutes once exposed to the conditions of the Antarctic interior. One of the simplest examples is batteries. Nearly all modern scientific tools rely on them. Sensors, drones, communication devices, drilling equipment, navigation instruments, cameras, measurement tools, robotic rovers, and countless smaller systems all depend on reliable power. But battery chemistry slows in cold environments, and Antarctica's deep interior is colder than any place most batteries are tested for. Even special cold weather batteries drain rapidly. A device with a full charge might last hours under normal conditions, but only minutes in 40, 50 or 60 degree temperatures. At 80 degrees and below, batteries can lose power so quickly that devices shut off unexpectedly. Researchers sometimes try to compensate by storing batteries inside their clothing to keep them warm, or by building heated compartments inside equipment. But both options introduce new problems. Heated compartments consume power, which shortens battery life even further. Storing batteries on the body helps only with small tools. Larger equipment can't rely on body warmth. And even when batteries do keep functioning, their lifespan shortens permanently from repeated exposure to such extreme cold. Electronics face similar issues. LCD screens freeze, touch screens become unresponsive, internal circuits slow or malfunction. Even simple circuit boards can crack when metal contracts in the cold. Wires stiffen, casings become brittle, and connectors become difficult to handle with gloved hands. For machines that rely on precise movements, like robotic drills or autonomous rovers, this brittleness can be catastrophic. A single crack in a sensor housing or a frozen joint can shut down an entire mission. Mechanics suffer too. Greases and lubricants thicken until they no longer move smoothly. Engines seize, pistons jam, gears struggle to turn, hydraulic systems fail, and these failures don't happen gradually. They can occur suddenly, without warning, with no chance to intervene. Even heavy-duty machines built for polar conditions require constant maintenance, and that maintenance becomes nearly impossible when temperatures drop low enough that wrenches freeze to gloves or metal burns fingers through protective clothing. Fuel behaves unpredictably as well. Diesel becomes sluggish, certain fuels gel completely, lines clog. Fuel tanks must be heated constantly to prevent freezing. Heating systems themselves require energy, and energy must be stored somehow, bringing the problem back to batteries and fuel again. It becomes a loop that engineers can't fully escape. Everything requires something else to stay warm, and everything risks freezing if one component falters. Even the simplest mechanical systems face problems. Plastic components that would bend easily at room temperature become stiff and crack. Rubber seals lose flexibility and fail to seal. Adhesives lose strength. And because the air is so dry, static electricity becomes more common, posing a risk to sensitive electronics. Some of the most advanced robotic systems ever built have been tested in Antarctica. Autonomous vehicles designed for polar exploration, ice-penetrating probes, lightweight drones, surface rovers meant to cross long distances with minimal human assistance. Many of these machines perform well in controlled environments, but once deployed into the deep interior, they encounter conditions that push them past their limits. Drones, for example, face multiple simultaneous challenges: cold air that reduces battery performance, wind that destabilizes flight, low visibility that interferes with navigation, and thin air that affects lift. As a result, drones often can't fly far, and when they do fly, their flight times are drastically shorter than expected. Similar problems face ground-based rovers. Some models freeze, others fail because sensors can't detect crevasses hidden beneath snow. Radar mounted on these rovers can be confused by reflections from compacted ice. In regions with deep crevasse fields, rovers risk falling into gaps just as easily as humans do, and even if they avoid physical hazards, The wind can bury them in drifting snow, covering solar panels or blocking communication antennas. Communication itself becomes a challenge. Satellite signals can be lost in storms, antennas freeze or crack. Transmission equipment can't be exposed too long without heating. Many remote regions sit far from existing stations, making it harder to maintain reliable connections. If a machine breaks down in one of these areas, it might be impossible to recover, or even to locate once the wind has erased tracks and covered it with snow. Drilling technology faces perhaps the most dramatic challenges. Drilling through Antarctic ice requires maintaining a borehole that doesn't freeze shut. It requires power sources that don't fail. It requires equipment that can withstand pressures that increase as the drill goes deeper. Traditional drills use fluids to keep holes open, but these fluids can contaminate subglacial environments. Clean drilling methods have been developed, but they are complex, slow, and expensive, requiring precise temperature control and constant monitoring. A small error can freeze a drill in place. Once stuck, the equipment may never be recovered. Even melting-based drills, designed to melt their way downward with heated water, face issues. The water can refreeze around the drill if circulation is interrupted. Heating systems require large amounts of fuel. The hoses that supply the heated water must remain flexible, yet exposed hoses can freeze if left still even briefly. This leads to situations where a team might spend weeks reaching a subglacial lake, only to risk losing all equipment because the drill froze or a hose cracked. For scientific instruments used to measure conditions within the ice or beneath it, the challenges continue. Sensors placed into boreholes can be crushed as the ice slowly closes the hole. Fibre optic cables freeze. Instruments meant to operate at specific depths shift as the ice flows around them. Anything placed inside the ice becomes part of a moving environment. You can't anchor something securely when the ground itself shifts over time. Instruments move, tilt, or become buried deeper than intended. Robotic submersibles face another layer of difficulty. A few have been designed to explore the water beneath ice shelves. These machines must navigate in total darkness, in cold water, under hundreds of meters of ice, surrounded by currents and unseen hazards. They rely on tether cables that can snag or freeze. If untethered, they risk losing communication entirely. If something malfunctions, there is no way to retrieve them. Several submersibles sent beneath the ice shelves have disappeared, lost in the dark beneath thousands of tons of ice. One of the most ambitious concepts in polar exploration is the idea of an autonomous rover capable of travelling across long distances on its own. Some prototypes exist, but none have crossed the most difficult regions of Antarctica. The terrain is simply too unpredictable, the wind too severe, the crevasse fields too dangerous, the temperatures too low for reliable electronics, the distances between safe zones too vast to support maintenance or repair, and because many of the unexplored areas lie far from any station, even delivering a rover to the starting point becomes a challenge. Even aircraft, which seem like the best solution for reaching remote regions, face limitations. The cold affects fuel. The wind affects stability. The elevation in the interior means thinner air, which reduces engine performance. Runways must be carved into snow or ice and constantly maintained to prevent drifting. In some regions, no runways exist at all, and because landing in deep interior conditions is risky, pilots must choose carefully where they fly. They cannot simply land anywhere they want, especially not in areas with unpredictable winds or heavy snowfall. Short-range flights also require backup plans in case of sudden weather changes. If the wind picks up unexpectedly or visibility drops, a pilot may have to return immediately. This limits how far they can travel into the continent's centre. Many remote areas lie beyond the safe radius of flight. Even if an aircraft could reach them, it couldn't land safely or rely on stable conditions long enough to deploy instruments. This creates pockets of land, large pockets, that aircraft simply cannot reach or study reliably. Satellite technology has helped fill some gaps, but even satellites face limitations. They can't see through thick ice. They struggle to interpret certain radar signals in extremely cold conditions. Snowstorms obscure surface details, and while satellites provide invaluable data, they cannot replace close-range exploration. They give us broad maps, temperature profiles, surface movement data, and other measurements, but they cannot answer detailed questions about what lies beneath the ice or within specific regions. As advanced as our tools are, they were designed for environments with boundaries, places where temperature stays within certain ranges, where wind has predictable limits, where the ground behaves like ground. Antarctica is different. It exists on the edge of what our technology can endure. The continent is cold enough to stall chemistry, dry enough to alter materials, windy enough to challenge aerodynamics, isolated enough to limit communication, and covered in ice that shifts unpredictably underfoot. Because of this, many parts of Antarctica remain untouched not just by humans, but by machines. Even the idea of sending autonomous probes into the deepest interior faces enormous challenges. Every component must survive conditions far beyond ordinary standards. Every piece must handle stresses that no test chamber can fully replicate. And even if a machine could operate reliably for a short time, the chances of long-term operation are slim. As it stands, our current technology can reach only a fraction of the continent. This limitation raises an interesting point. Perhaps some remote regions will remain unexplored not because we lack creativity, but because pushing deeper would demand tools so durable, so energy efficient, and so adaptable that they would need to perform beyond what is needed anywhere else on Earth. Building such tools may be possible someday, but designing technology specifically for environments harsher than anywhere else on the planet requires resources and motivation that don't always align. There's also the question of whether exploration is worth the risk of equipment loss, environmental contamination, or human danger. Just because a region can potentially be reached doesn't mean it should be. Some areas may remain unexplored simply because reaching them could cause more harm than scientific value. Technology isn't just limited by physics, it's limited by ethical considerations as well. And that brings us to the next part of the story. Because even if technology could conquer every physical challenge Antarctica presents, even if machines could withstand the cold and survive the winds and cross the ice and reach the deepest interior, there is still another barrier, one not made of temperature, weather, or terrain. It's a barrier created by people, by agreements, by principles, and by the shared understanding that some places require protection, not intrusion. And that is where we go next, into the question of why not exploring certain places can sometimes be the right choice, even when curiosity pulls us forward. For as long as people have wandered across the Earth, curiosity has been one of the strongest forces guiding exploration. It has pulled humans across oceans, into jungles, up mountains, and through deserts. It has driven countless questions, bold expeditions, and discoveries that changed how we see the world. But standing in front of Antarctica's most unreachable places, regions hidden under kilometers of ice, ecosystems sealed away for millions of years, landscapes that shift and reshape under relentless cold and pressure, curiosity runs into something it rarely encounters, the possibility that the most responsible decision is not to go farther. The idea of choosing not to explore feels strange at first. It goes against the instinct to push boundaries. But Antarctica is a place that forces people to rethink what progress means. It raises questions about the responsibility humans carry when approaching environments that have remained untouched for longer than human history. It places value not just on what we could learn, but on what we might disturb by trying to learn it. Part of this comes from the continent's fragility. Even though Antarctica seems harsh and hostile, many of its environments are surprisingly delicate. The ice might look solid and eternal, but beneath it lies water that reacts to the slightest change. Microbes living in sealed lakes exist in chemical balances so precise that a tiny shift could reshape the entire ecosystem. Rock formations buried under ice may contain records of ancient climates that could be damaged by drilling. Sediments in subglacial basins hold information about long-lost environments, but those sediments can be disrupted by a single contaminated sample. This fragility forces researchers to ask a difficult question. Is the knowledge gained from disturbing these environments worth the cost of altering them? For some, the answer is no. Many scientists argue that certain regions of Antarctica should be left alone, not because they dislike exploration, but because they understand how easily human presence could change something that has remained stable for an unimaginable span of time. If a drilling project carried microbes from the surface into a subglacial lake, the contamination might go unnoticed for years before its effects became clear. If equipment introduced heat, chemicals or pressure changes into an isolated environment, it could disrupt conditions that have persisted for millions of years. In this sense, some unexplored places in Antarctica remain that way, not because we lack the technology, but because the risks outweigh the rewards. The rules governing activity in Antarctica reflect this understanding. Unlike most of the world, where borders are defined and nations control their own territories, Antarctica operates under a unique agreement, the Antarctic Treaty. It was formed not to divide the continent, but to protect it. It prohibits military activity. It restricts mining. It prioritizes scientific cooperation, and it places strict limits on activities that could harm the environment. This means that any attempt to explore certain regions must be justified by strong scientific reasoning and conducted with extreme care. These rules exist not to stop discovery, but to ensure that discovery does not come at the expense of the continent's integrity. They acknowledge something important, that Antarctica is more valuable as a preserved environment than as a resource to be consumed or a frontier to be conquered. And within those guidelines lies another truth, that some places might be best left unseen. Certain areas beneath the ice are already designated as protected zones where human entry is prohibited unless absolutely necessary. These zones include some of the most sensitive ecosystems on the continent. They are marked not by fences or signs, there is no need for that, but by agreements among nations that respect the importance of leaving them undisturbed. In these regions, exploration would risk more than physical danger. It would risk erasing information about Earth's history, altering biological systems, or causing lasting environmental damage. This perspective doesn't come from fear. It comes from respect. Respect for the age of these environments. Respect for their isolation. Respect for the idea that not all knowledge must be acquired through direct contact. In a world where nearly everything can be mapped, photographed, measured and catalogued, there is something meaningful about allowing certain places to exist without interference. There's also the question of precedent. If one country or research team were to push into a protected zone despite the rules, it could encourage others to do the same. Competition might grow. The desire to be the first to reach a hidden lake or buried mountain could overshadow the responsibility to preserve the environment. By agreeing to leave certain regions untouched, the global community avoids turning Antarctica into a battleground of ambition. It remains a place where cooperation takes priority over conquest. Even when exploration is allowed, it must be done with caution. Every team must consider not just what they hope to learn, but what footprint they will leave behind. This applies to drilling, sampling, travelling across the surface, and even setting up temporary camps. The smallest mistake, a spilled fuel container, an improperly cleaned drill, a cracked hose, could introduce contaminants that remain in the environment for decades. In places where wind and snow quickly erase visible traces, chemical or biological traces can still linger unseen. For this reason, many researchers emphasize that exploration must be balanced with restraint. The goal is not to reach every corner of the continent, but to learn what can be learned without harming what exists there. Sometimes that means turning back before reaching a destination. Sometimes it means relying on remote sensing instead of direct sampling. And sometimes it means accepting that certain questions will not be answered. This acceptance requires a shift in how we think about discovery. It replaces the idea of exploration as conquest with the idea of exploration as stewardship. It acknowledges that humans have the power to alter ecosystems dramatically, even unintentionally. It recognizes that curiosity, while powerful, must be tempered by responsibility. It also acknowledges something deeper, that the world does not exist solely for human understanding. Some places exist for themselves. They have their own histories, their own rhythms, and their own significance independent of what humans can learn from them. In this way, the ethics of leaving places unseen becomes an extension of respecting the planet. Antarctica is one of the last places where this perspective is widely accepted. It stands apart from most regions on Earth because it does not belong to any one nation. It belongs in a sense to everyone and to no one. And that shared responsibility creates a space where decisions can be made for the sake of preservation rather than exploitation. It's easy to imagine the temptation of being the first to reach a particular hidden valley, or to drill into a lake that has never encountered the open air. The scientific possibilities are vast, but every potential discovery carries a cost. Once disturbed, these environments cannot return to their untouched state. Once contaminated, they cannot regain the conditions that made them unique. This is why so many researchers approach Antarctica with a mindset that prioritizes caution. In many ways, this restraint mirrors the continent's own nature. Antarctica endures because it changes slowly, quietly, without sudden disruptions. It operates on a timescale that far exceeds human lifetimes. Its ecosystems have survived because they are sheltered from many of the forces that shape the rest of the planet. And by choosing to leave certain areas unseen, humans acknowledge that they need to adapt to Antarctica's pace, not force Antarctica to adapt to theirs. This mindset also shapes the future of research. As technology improves, the ability to reach more remote parts of the continent may grow. Autonomous systems might become more durable, drills might become cleaner, sensors might become more accurate. But even if every technological challenge was solved, the ethical questions would remain. Should we reach into every hidden lake? Should we expose ecosystems that have survived in isolation for millions of years? Should we remove sediments that hold the record of ancient climates? Or should we preserve these environments as they are? These questions don't have simple answers. They require weighing curiosity against responsibility, potential discovery against potential loss. They invite discussion among scientists, governments, and environmental experts. They place emphasis not just on what we want to learn, but on what we might damage by learning it. Antarctica forces these questions in a way that few other places do. There are other remote or fragile environments around the world, but none combine the scale, isolation, and scientific significance of Antarctica's hidden regions. And because access is limited, every decision carries enormous weight. Exploring a region once may make it impossible to study that region again in its original state. A single expedition might alter conditions that took millions of years to form. Yet, despite all of these concerns, curiosity does not disappear. It changes shape. Instead of focusing on reaching the unreachable, it turns toward understanding how to observe without disturbing. It inspires the development of new tools that can gather information from a distance. It drives the creation of careful guidelines that balance research with conservation. It shifts the goal from conquering the unknown to protecting it. This evolution in perspective reflects a broader understanding that untouched environments have value beyond the data they hold. They serve as reminders of how much of the planet still exists beyond human influence. They represent a world where nature continues without interruption. And they challenge humans to consider their place in that world. This shift also sets the stage for what comes next, because even if humans leave certain regions unseen, the continent itself will continue to change. Ice will move, winds will reshape the surface, lakes will drain and refill, hidden ecosystems will evolve in ways we may never witness, and as the planet warms, Antarctica may reveal some of its secrets on its own, and hide others more deeply. That sense of uncertainty brings us naturally toward the final part of this journey. Because understanding why some places will remain unexplored also means understanding how those places will change in the future, and what it means for a continent that has always seemed frozen in time, yet is moving toward a world that will challenge it in new ways. Let's continue there next, into what the future holds for the last untouched regions of Antarctica. When thinking about the future of Antarctica, it's easy to imagine that the continent will stay the same forever. It looks timeless, it feels ancient. The ice seems immovable, the winds eternal, the cold unchanging. But Antarctica has been shifting and evolving for millions of years, long before humans ever thought about mapping it, studying it, or setting foot on its surface. And long after we're gone, it will continue to change in ways that don't always match what we expect or want. The hidden parts of the continent, the inaccessible basins, the sealed lakes, the buried mountain ranges, the zones where technology falters, the protected regions where ethics demand restraint, they all exist as pieces of a landscape that looks frozen, but is quietly, steadily transforming. Some of these changes will come from forces that have shaped the continent for ages. Ice will continue to flow outward under its own immense weight. Winds will keep carving patterns into the surface. Snow will gather and erase tracks. Crevasses will open and close. Lakes will fill and drain beneath the ice sheet. Entire regions will shift subtly as the land beneath rebounds or sinks under pressure. Even if humans never explore these remote areas directly, the continent itself will keep moving around them, covering and uncovering pathways, reshaping the surface and the depths. But the future of Antarctica will also be shaped by global forces that reach far beyond the continent. Climate patterns, ocean circulation, and atmospheric changes will all play roles in determining how much of the ice remains stable and how much becomes vulnerable. Even the most remote, unreachable parts of the interior will feel these changes eventually, even if not in the ways we might picture. It won't always look like melting or thinning. Sometimes it will look like shifting stress patterns, changes in snowfall, or subtle differences in temperature that alter how the ice moves and where pressure builds. There's a strange tension in imagining Antarctica's future this way. On the one hand, it feels like a place completely insulated from the rest of the world. On the other hand, it's part of a global system too interconnected to ignore. A warmer world affects the oceans that lap against Antarctica's ice shelves. Changes in wind patterns influence the cold air that flows across the plateau. Shifts in precipitation alter snow accumulation at the surface. Even slight temperature increases in some regions can change how fast ice moves toward the coast. And while the deep interior may remain cold enough to avoid drastic warming for a long time, the edges of the continent may shift in ways that ripple inward slowly, almost imperceptibly. These changes raise questions about whether Antarctica's most hidden regions will stay hidden. If the ice sheet thins over centuries, landscapes buried beneath could eventually rise closer to the surface. If ice shelves weaken, the flow of inland ice could accelerate, altering the movement of subglacial water or exposing new areas to exploration. But even if some features become more accessible, others may become more dangerous. Faster moving ice could create more crevasses. Thinner ice could become more unstable. Lakes could drain more frequently. Regions once considered stable might become unpredictable. There's also the question of whether new technologies will change what's possible. Engineers continue to design machines that can handle harsher environments. Power systems may become more efficient. Autonomous vehicles might survive longer. Materials might be developed that resist cracking in extreme cold. Drones could fly farther. Robotics could advance to the point where exploring beneath ice shelves or deep within crevasse zones becomes feasible. But even as these tools improve, the environment will continue to push them to their limits. Antarctica will remain one of the hardest places for technology to operate, simply because so many forces converge there. Cold, wind, dryness, pressure, isolation, shifting surfaces, and fragile ecosystems that require caution, it's possible that one day specialised instruments will reach some of the places we can't study now. A robot might explore an isolated subglacial lake without contaminating it. A drone might map a crevasse field with perfect precision. A probe might descend through ice kilometres thick without freezing or breaking. New communication systems might allow data transmission from areas where storms and terrain block current signals. These advances could open windows into regions that have remained closed for human understanding. But even if technology opens some doors, others will likely remain shut. Not because humans are incapable of reaching them, but because the choice to leave them undisturbed will still matter. Ethical considerations won't disappear. In fact, they may grow stronger as more becomes possible. The question won't just be, can we explore this, but also, should we? The value of untouched environments might increase as the world becomes more crowded and more studied. Antarctica may become one of the last places where the idea of leaving something unseen holds real meaning. And that raises another point about the future, the importance of preserving uncertainty. In a world where almost everything can be measured or photographed, the unexplored parts of Antarctica feel like a reminder that not all mysteries need to be solved. Some of them serve a purpose simply by existing. They give scale to our understanding of the planet. They show that even with satellites, sensors, drones, and global networks, there are still places where nature remains in control. There is something grounding about that. Something that pushes against the assumption that humans must understand and access every corner of Earth. The unknowable aspects of Antarctica's future aren't limited to ice and climate. They also extend to how people will relate to the continent. Will future generations adopt the same protective mindset that guides research today? Will the Antarctic Treaty remain intact? Or will shifting world priorities threaten its principles? Will new nations seek access to resources buried beneath the ice? Will scientific cooperation remain the central pillar of activity in the region, or will competition grow? For now, the treaty stands strong, and the global scientific community remains committed to preserving the continent. But Antarctica's future depends not only on environmental stability, but on human decisions. If those decisions value preservation over exploitation, then many of the continent's hidden regions will remain untouched. If priorities shift, entire areas that were once off limits could become targets for drilling, mining, or resource extraction. The tension between protection and opportunity is likely to grow as technological capabilities evolve. It is in this tension that Antarctica's future becomes truly unknowable. The continent changes slowly, yet the decisions surrounding it can change quickly. One policy shift, one technological breakthrough, one new discovery could alter how nations view the frozen South. Human influence has a way of reshaping landscapes even from a distance. The question is whether that influence will expand or remain controlled. Still, even imagining a future in which exploration becomes easier, or in which global pressures push nations to reconsider boundaries, there will always be places that stay inaccessible. Some regions lie too deep beneath the ice. Some lakes are too sensitive to approach without causing harm. Some crevasse fields are too unstable. Some winds too relentless, some temperatures too extreme. There will always be corners of Antarctica that resist intrusion simply because the continent itself maintains its power. And in that resistance lies part of what makes Antarctica unique. It's a place that pushes back against human reach not through hostility, but through scale, age, and silence. It sets limits without speaking. It offers knowledge but keeps some secrets. It challenges curiosity without dismissing it. It forces a slower pace, a more careful approach, a deeper respect for what exists beyond our immediate understanding. As the world changes, Antarctica will continue to be a place where those contrasts remain clear, a place where the known and unknown sit side by side, a place where technology advances but nature stays ahead. A place where human ambition meets environmental boundaries. A place where the most remote landscapes remain untouched. Not because no one cares about them, but because so many people understand their value. There's something fitting about ending this journey not with answers about Antarctica's future, but with the acknowledgement that some aspects will always remain uncertain. The continent doesn't promise full understanding. It never has. Instead, it offers a reminder that mystery still exists in the world, and that respecting those mysteries is part of living on a planet that doesn't belong to us alone. The ice will shift, the winds will change, lakes will rise and fall, mountains will stay buried, creatures will adapt in darkness, technology will advance, policies will evolve, curiosity will persist, and somewhere beneath all of that, in regions no person will ever see directly, the story of Antarctica will continue in silence, moving at a pace so slow and so steady that it makes the present moment feel small by comparison. That sense of scale, of looking at a world that stretches beyond the reach of exploration, may be the clearest view of Antarctica's future we can have. It isn't a future defined by conquest or complete understanding. It's a future defined by patience, restraint, uncertainty, and the possibility that some places remain special precisely because they are beyond us. And as the ice continues its quiet movement, as the winds carve new shapes into the snow, as the unseen lakes breathe in darkness, as the continent shifts under its own weight, Antarctica's future will stay what it has always been. Unknowable, untouched in places, and powerful in ways that don't need to be witnessed to be real.